My name is Matt Bruin, and this is Lab 3 for Dr. Fenton's Physics 1 class. So the purpose of this lab was to visualize the motion of a nonlinear object moving through space in a parabolic or elliptical motion in this instance with a non-contact force. So obviously this force is gravity throughout space. And with this, it's kind of understanding forces acting on an orbiting body with a relative static body. Obviously, the black hole can be orbiting something else, but in this instance, we're calling it static for the purpose of the simplicity of this lab of origin. And of course, when you're working with forces and finding these forces, you can formulate the mathematical equations that can then give you the constants such as velocity, momentum, and then actually we're going to work through it until we find the mass of the black hole, which is the pinnacle. So the fundamental physics in this problem is here we have elliptical motion charted by this, and these are actually the same. This is its initial point and its final point told by point initial and final. This is the radius in between these 2 points, initial radius, final radius, and then here are the forces that are actually most important in this lab. So we have parallel force initial and perpendicular force initial. And perpendicular forces are the tangential to the curve of motion, and parallel are in line with the normal force, so directly back to its source. In a free body diagram, of course, this is typically going to be gravity that's holding it down, or tension on the ball. And of course, here is the direction of motion charted by the arrows, such as like polar coordinates. And then we have our final. And these obviously are not congruent radii. Therefore, these forces are not the same. So, as we can tell by the equations we will go over, is when the radius is smaller, the force is actually much greater. So that means that parallel force final is greater than parallel force initial. And we can tell that by the velocity components. So first we're going to find the velocity components of the formula, which is given by this equation, and the mass of the orbiting body and the gravitational constant are given. All that we have to leave up is the radius from the black hole, and that's just given in the Python code simply. And then of course, to find the x and y components, we can break that down, mass times velocity, in order to find the momentum. And then we can work through them all the way in order to find the mass of the pivoting body, which is the black hole, and getting that by this formula. So velocity squared times the radius over the gravitational constant. And this is a simulation of what it looks like. So as you can tell, and as mentioned before, because this force is greater, it is actually going faster around this region of the Earth. So its velocity is not constant throughout its entire motion. And this is because parallel forces are what control its velocity or direction, and it is moving throughout the entire thing. And then, in order to understand kind of how this applies to everything, the difference in net forces and its change in momentum are actually pretty easy to visualize. So F net we can see as it changes, but the change in momentum we can't. So if we go back to this animation, F net is this direction of acceleration. And that's boom, boom, here. It's where it's going. But the momentum on the other hand is where it's trying to go. So it's changing momentum. It's this direction. It's, hey, let's turn that way to pull it back into the circle. So simply put, F net we can see, changing momentum we can't. And if it was a different black hole, of course, we'd be able to tell the difference, because if the masses were different, therefore the gravitational force would be the same. If the body were to have, if the black hole were to have a greater mass, therefore its gravitational pull would be much greater, and this would be much closer in radius, and therefore the orbiting star body would be going much faster.